For 4.5 billion years, our sun has poured out light, heat, and magnetic fury. Yet for almost all that time, humanity had seen only its familiar equatorial face. Astronomers photographed titanic flares, watched sunspots drift lazily across the disk, and charted fiery loops rising like cathedral arches. But they did it all from a single flat vantage. We lived in the ecliptic plane, an imaginary disk slicing through the solar system like the brim of a vast cosmic hat. And so every probe, every telescope, every eye saw the sun mainly from the waist up. We understood the sun's broad strokes, but its hidden poles, the very hinges of its magnetic machinery, remained a blank map. Then, early in 2025, something extraordinary happened. A joint ESA-NASA spacecraft called Solar Orbiter, after 5 patient years of orbital ballet, tilted far enough below the solar equator to photograph the never-before-seen South Pole. The images were staggering: shimmering plumes taller than Earth, twisted funnels of magnetized plasma, vast dark canyons called coronal holes, and bright snaking sheets of electric fire. In one mosaic shot, the spacecraft's extreme ultraviolet imager pulled back the curtain on the lower hemisphere of our star, revealing details no human had witnessed. Today we will take an unhurried journey through that achievement, why it matters, how engineers made it happen, what those first pictures reveal about the next peak in solar activity, and how knowledge won at the poles will soon protect everything from astronauts to power grids. To understand why the sun's south pole is so hard to observe, imagine the solar system suspended in an invisible dinner plate. The planets, birthed from a spinning disk of gas and dust, inherited that flattened shape, so Earth, Mars, and the rest all orbit in roughly the same plane. Our spacecraft generally launch from that plane as well. Look at the sun from an orbiter near Earth, and you stare almost exactly at its midriff. Over the centuries, astronomers made clever attempts to cheat the geometry, scanning the limb as the sun rotated, combining helioseismology with math to reconstruct the hidden regions. But those techniques were like trying to sketch a mountain range by listening to echoes alone. True reconnaissance demanded a probe that could claw its way above and below the plate. Yet boosting a spacecraft out of the ecliptic costs enormous energy. A rocket must not only hurl the craft toward the sun, but also yank it off the highway of planetary orbits. The engineers behind Solar Orbiter adopted a slower, subtler plan. Enlist the help of Venus, the planet that orbits inboard of us, to gravity assist the probe into a gently tilting path. Picture it. February 2020, Cape Canaveral. A Falcon 9 roars into the night carrying a washing machine-sized spacecraft wrapped in white foil. Once free of the second stage, Solar Orbiter unfurls golden solar panels and begins its long commute. 6 times it will swoop past Venus. Each flyby is a skateboarder's pump in a half-pipe. The craft trades a pinch of orbital speed for a precious change in inclination. Over years, the pump grows stronger. By late 2024, the probe reaches an angle of about 15 degrees below the solar equator. On 23 March 2025, while most people on Earth were still yawning through the equinox week, Solar Orbiter's ultraviolet camera trained its lenses downward and took the first clear portrait of the southern pole. The science team in Darmstadt and at NASA's Goddard Center watched raw data stream across space, a mosaic of 22 panels stitched into one breathtaking panorama. Where textbooks once showed an empty circle, the monitors now glowed with motion. Great fountains of plasma, called polar plumes, rose in blue-white sheets. A yawning coronal hole, darker than ink, beckoned solar wind into the heliosphere. Most startling of all were miniature tornadoes. Corkscrew jets, linking surface to corona, their diameters dwarfing continents, spinning at hundreds of kilometers per second. For a moment, the control room fell silent, the hush that accompanies raw discovery, and then erupted in applause. Why did these images matter? Because the sun's magnetic fields, the invisible threads that twist and snap to produce flares and coronal mass ejections, are seated at the poles. Our star undergoes an 11-year cycle in which its global magnetic polarity flips, like a giant bar magnet turning inside out. As the solar dynamo revs, fresh flux migrates from mid-latitudes toward the poles and sinks back toward the interior. Think of conveyor belts carrying magnetic cargo. When we lacked clear pole data, dynamo models were guesswork. With them, scientists can now track the birthplaces of future storms. Those storms unleash charged particles that slam Earth's magnetosphere, stirring brilliant auroras, but also tripping transformers, degrading satellite orbits, and forcing astronauts to shelter in radiation shadows. In 1989, a solar storm collapsed Quebec's grid in 90 seconds. In 2022, a comparatively mild eruption dragged dozens of newly launched Starlink satellites into fiery re-entry, costing millions. Knowledge from the pole will let us forecast eruptions earlier, choose safer launch windows, and harden vulnerable circuits. The path to those forecasts winds through engineering marvels. Solar Orbiter must stare at a surface glowing at 5,500 degrees Celsius, while keeping delicate electronics cool enough for laptop-grade circuits. Its heat shield is a sandwich of titanium, carbon fiber skins, and a flaky black coating called solar black that shrugs off ultraviolet assault. The front panel looks like a cheese grater. Dozens of tiny apertures allow instruments to peek, while all other sunlight ricochets harmlessly away. A heat pipe network wicks residual warmth to radiators that face perpetual night. Even with that armor, the doors can open only sparingly, because each observation session is a controlled flirtation with destruction. Meanwhile, on the end of a boom bristles a magnetometer that must taste feeble magnetic whispers without interference from the spacecraft's own wires. Engineers painstakingly mapped each screw's magnetic signature, banning any alloy that might murmur louder than the field they hope to hear. Inside this modest bus ride, 10 separate instruments collaborate. The extreme ultraviolet imager paints the sun in million-degree light. SPICE, the spectral imaging of the coronal environment, sniffs elemental fingerprints. Polaris measures solar wind protons that splatter like invisible rain. Together, they transform the probe into a multimodal eye, one that sees structure, chemistry, and weather in a single frame. Yet the craft must survive 10 years at least, enduring radiation equal to a lifetime worth of dental X-rays each week, and solar storms that rattle gyros like dice. To prepare, mission planners simulated worst-case coronal mass ejections and commanded the probe to spin slowly, turning solar panels edge-on to the blast. That metallic yoga reduces drag and avoids current surges that might cook a circuit board faster than solder melts. As engineers dealt with physics, the science team faced the calendar. Solar cycle 25 is surging toward maximum in 2025-26. Historically, strong maxima produce snarls of sunspots and a blizzard of eruptions. Forecasters worry because modern civilization depends on technologies acutely sensitive to space weather. Precision agriculture relies on centimeter-accurate GPS. Airlines plot polar routes that save fuel but expose avionics to radiation. Even cryptocurrency miners fear voltage spikes. By imaging the South Pole at this moment, Solar Orbiter gives modelers a head start. Already, data are feeding into NASA's Space Weather Prediction Center, where neural network algorithms cross-reference flux transport with disk imagery to issue 3-day geomagnetic storm bulletins. The goal is to stretch that timeline to 1 week. A shipping company would reroute cargo. A satellite operator would switch off non-essential electronics. A power utility would spin up reserve turbines. Every extra hour of warning is money and safety saved. Of course, Solar Orbiter is only one player. Closer still to the Sun, moving on a comet-like orbit that dips inside Mercury, screens the Parker Solar Probe. Parker's heat shield experiences nearly 1,400 degrees, but its instruments reach within 10 solar radii, close enough to fly through the birthplace of solar wind. Where Solar Orbiter peers from above, Parker samples from within. In late 2025, Parker will intersect magnetic field lines that connect back to the very South Pole coronal holes revealed by Solar Orbiter. That handshake will let researchers calibrate remote sensing against in-situ plasma counts, a ruler laid across the electromagnetic storm. Meanwhile on Earth, the Daniel K. Inouye Solar Telescope in Hawaii photographs photospheric granules as small as Manhattan, bridging scale from pole to pixel. Put the data together, and you have a multi-layer cake of solar knowledge, from convective rumble in the belly to wind screaming into interstellar space. Now tilt your imagination further forward. By 2029, after 3 more Venus flybys, Solar Orbiter will reach 25 degrees inclination. That may not sound dramatic, but compare it to the view from Earth, 0 degrees, and the difference is like trading a curb-level photo of a skyscraper for a rooftop drone shot. The poles will appear less foreshortened, details sharper. At times, the spacecraft will watch solar storms erupt from behind the limb and fly straight over the polar cap, mapping how field lines twist from origin to outflow. And beyond 2035, mission planners envision the Solar Polar Imager, a sister craft that would ride a monumental Jupiter gravitational assist, shedding sideways momentum like a snowboarder banking an impossible turn, ultimately climbing to a 90-degree polar orbit. From that perch, cameras could stare continuously at both poles, sending real-time movies of the solar dynamo's gears. It is a bold dream, but recall that until 1990, sending a probe to orbit Jupiter sounded mad, and yet Galileo did it. Tenacity has a way of redesigning impossible. Let's pull back and ask how the public will feel these discoveries. Start at ground level. Electric grid managers subscribe to alerts from the Space Weather Prediction Center. Already, early South Pole data nudged warning models, triggering test drills in mid-2025. In California, an investor-owned utility loaded spare transformers onto flatbed trucks positioned near high-risk substations. In Scandinavia, operators rerouted extra hydropower to compensate if DC links tripped. At 37,000 feet, pilots flying from New York to Tokyo weigh polar radiation counts. High counts cut goose flights downward over Anchorage, lengthening journeys but slashing radiation doses. In the future, real-time pole imagery might let flights thread safe gaps between storms, like skiers finding fresh powder. On low Earth orbit satellites, reaction wheels are delicate. If a CME is predicted to hit, operators shift craft to safe mode. Without the new data, warnings are vague. With pole-fed models, false alarms shrink, and satellites stay online longer, saving billions. Then there's human spaceflight. In 2025, NASA's Artemis 3 aims to land astronauts near the Moon's south pole. Unlike Apollo crews, they may remain for days exposed to cosmic weather with only thin aluminum shells. Solar Orbiter's Vantage lets mission control watch flares that might hurl lethal particle showers toward cislunar space. 10 or 20 hours of notice could spell the difference between a calm EVA and a scram into the lander's radiation vault. Farther ahead, Mars explorers may spend years without magnetospheric protection. The protocols we test now with lunar crews, escape caves, portable storm shelters built of polyethylene and lunar regolith, will rely on polar forecasting even more. Not all impact is profound, some is simply delightful. Amateur aurora hunters track the KP index on smartphone apps. When Solar Orbiter's imagery shows a South Pole coronal hole yawning Earth-facing, fans from Michigan to Tasmania pack cameras, drive to dark skies, and point lenses at curtains of green and violet that ripple across midnight. Science fuels wonder. Wonder fuels public support. Public support funds the next daring mission. It is a virtuous cycle, powered by photons born in the sun's core 8 minutes before they reach us, filtered through human curiosity. Let's linger a moment on the images themselves. Scientists color-coded them in extreme ultraviolet, deep blues for one spectral line, sizzling whites for hotter iron emission. The South Pole coronal hole yawned darker, a skylight into the lower corona. At its rim rose spires, plasma jets riding open field lines, some angled sideways, shepherding solar wind into a spiral that would weeks later graze Earth. Trace field line models. Overlay them with Parker Solar Probe dust counters and you have a fingerprint linking a bright speck on a mosaic to vibrations detected millions of kilometers away. That chain of reasoning makes heliophysics a detective story. Clues, alibis, and eventual confession from a star. Now shift from data to philosophy. In the 14th century, Dante wrote of a mountain at the pole unreachable by mortal sailors. For millennia, the Arctic and Antarctic were blank dragons on maps. Gradually, human expeditions filled those voids. Now we repeat the exercise on the astronomical scale, charting the polar provinces of a star. Each new map humbles us. We thought we knew what the sun was, but we saw only 2/3 of its surface. We argued how the dynamo flips, but lacked direct views of the crankshaft. Discovery extends ignorance just as it extends knowledge, pressing questions outward like ripples. How many more mini tornadoes whirl unseen? Does north mirror south, or harbor asymmetries that steer cycles? Could predicting those differences help forecast century-scale grand minima, like the Maunder minimum that chilled Europe in the 1600s? These puzzles keep solar physicists awake at night and attract fresh graduate students who might otherwise chase exoplanets or quantum ships. Behind the science are the unsung craftspeople, mission designers plotting Venus swing-bys with coffee-stained notebooks, technicians bonding heat shield tiles under clean room lights, programmers writing onboard autonomy code so the spacecraft can close doors when radiation spikes faster than Earth can command. Each picture owes its existence to thousands of quiet decisions made right, each solder joint that passed vibration tests, each line of code that slid into memory with no off-by-one bug. When the first South Pole mosaic popped onto screens, some of those engineers wept. They had mortgaged years of nights and weekends to something intangible, and suddenly there it was, blazing proof that the gamble paid off. Our narrative would feel incomplete without acknowledging risk. Solar Orbiter flies on finite hydrazine. A micrometeoroid could pit its shield. A single flipped bit in flash memory could garbled instrument commands. Mission teams run contingencies, upload patch files, rehearse safe mode exits, keep at least 2 flight dynamics specialists on call during every perihelion. Even success can doom. Extreme ultraviolet detectors degrade under constant bombardment. Engineers added calibration lamps to track aging, but eventually the pixel well will shallow, dark current will rise, and images will fade. Before that day arrives, every bit of data is precious, yet data alone is inert. Transformation comes when modelers plug those pixels into dynamo simulations, when forecasters feed flows into ensemble cones, when grid engineers rewrite risk models. In late 2025, the US Department of Energy will begin using pole-constrained forecasts to index transformer insurance rates. A storm that once threatened $70 billion in damage might now inflict half. Multiply savings globally, and the value dwarfs mission cost. But even if dollars did not add, the cultural value would. We humans woke earlier than any species, looked at a star, and decided to send cameras to see what no eye could see. That is the signature of our species. So where do we go from here? Over the next 2 years, Solar Orbiter will deliver seasonal pole snapshots. Paired with helioseismology from the Solar Dynamics Observatory, scientists will watch magnetic flows advect toward the pole like rivers of iron filings. Every snapshot is a frame in a time lapse. Already, machine learning algorithms identify active region seeds days before they breach the surface. Combine that with polar plume brightness and coronal hole width, and models predict how much solar wind a region will spit. Each prediction is verified by ACE and DSCOVR satellites parked at L1, then refined. The model learns. Polar data make it learn faster. By 2027, when the spacecraft swings to 22 degrees inclination, the South Pole view will show the cycle declining. Sunspots will migrate equatorward while the polar coronal hole shrinks. A calm after the storm. In that lull mission, planners hope to test high-latency downlink modes, storing massive raw movies on board and dribbling them to Earth when antenna time freeze. Those movies may reveal convective cells the size of Texas, jostling at the pole like hexagons on Saturn, but made of boiling hydrogen. A decade ago, we did not suspect such patterns. Meanwhile, students at small colleges will download public solar orbiter frames and, with cloud computing, build open-source flare predictors. A teenage coder in Nairobi might write an app that pings fishermen before a geomagnetic storm that could confuse GPS. The benefits diffuse across borders, across economies, across cultures. Science done for curiosity protects livelihoods oceans away. I invite you now to stand on an imaginary catwalk above the sun's south pole. Look down. Below you the corona shimmers, a translucent veil rippling in electromagnetic wind. Streamers extend into space like frayed ropes, Every 11 years, the pattern reverses, ropes fold, tangle, and snap. Under that veil, deeper than we can see, churning plasma generates magnetic fields, loops them outward, and flings them toward us. We ride that weather, sometimes lucky, sometimes bruised. Seeing the source with our own instruments is like finally glimpsing the headwaters of a river that floods our valley. Knowledge is power, and wonder, and responsibility. When solar orbiter's first pole mosaic reached Earth, the mission's project scientists said, "We will never see the sun the same way again." He meant not just scientists, but all of us. Because once an image exists, once you have held a photograph of the star's hidden hemisphere, the mind refuses to return to ignorance. The cosmic map is larger, and the blank circle at the bottom of countless solar posters is now filled with detail and motion and beauty. So mark this moment. The long night of polar ignorance is ending. The next time an aurora ripples overhead, think of the plumes that seeded the storm, whispering from a pole now within human sight. Think of Solar Orbiter carving its lonely loop, Venus nudging it millimeter by millimeter higher out of the ecliptic. Think of engineers who will next target the North Pole, and beyond that, the far side of the sun hidden by its own mass. We advance one vantage at a time. Each fresh angle writes a new lost page of science and then delivers it found, cataloged, and shared. And when you feel the warmth of daylight on your skin, remember that the photons began their journey in a boiling equator, but their paths were sculpted by magnetic fields born at the poles, fields we now meet, at last, face to face. The sun grants life, threatens technology, and inspires awe. Thanks to a small spacecraft and a stubborn human will to explore, we finally greet the star in full, and it greets us back in ultraviolet brilliance. Stay curious, the story continues.